So the way that I might propose to do this is to say that terminal alkyne would be problematic, that it's acidic, and that I'm trying to have an alcohol be acidic, and maybe that's a compatibility issue. So I should not have a terminal alkyne by the time I'm reacting with that alcohol. And so the way that I can get around that is to say, okay, let me deal with the alkyne stuff first, and then I'll deal with the alcohol stuff after that. So I could instead start with something like I'll do my alkyne. The first thing I'm going to do is add the two carbons over here. That is going to give me this again. And then I can react with my strong base and a different well after that. So I'll just do this. And that would give me this. That means there's not going to really be reactive because it's just electrophilic at that carbon. And then I don't worry about compatibility with my alkyne. Both of those routes are pretty decent. You could make an argument that this won't be much of an issue. But if I were going in the lab and doing this, I would not want to have a potential compatibility issue. The key on something like this is that we want to be able to look at a molecule and figure out what types of bonds we know how to form. And so, like as an example, if I were trying to build this guy, if I were trying to do that in the same kind of field where I need to use like 3 carbons or fewer in my synthesis, what I want to be able to look at this molecule and say is that, for example, I know bonds that have carbon or bonds that I know how to form. That's the way that reaction. So if I look at that molecule and I see an alcohol present, I can always form the carbon-carbon bonds that are around that alcohol slowly that me down to similar starting materials. And then also now we introduce epoxides into our reaction, our 12-ox. And so that kind of expands the possibilities. So if I think about using an epoxide as an electrophile, if I can say, well, if that's that, think about where that oxygen ends up there. It doesn't end up right where that new bond is forming. It ends up right next door to that new bond. And so now when I see that alcohol, I can also think, well, that's a bond I can form if I was using an epoxide, or that's a bond that I can form if I was using an epoxide. And then we can think about when we do see an alcohol, we can picture that that could come from an alkene in various positions. All those types of reactions we want to be able to think about, like what types of bonds are possible. We're going to extend that list one more time with the next reaction that we're going to talk about. So your screen is like watching lights at me moment. Okay, very strong. Alright, so we have one new reaction in this module. It is alpha alkylation. So this is going to give us a new type of bond that we'll be able to form. So alpha alkylation, we're just going to take a simple ketone and we're going to use the generic base for the moment. When that base comes in, it can deep elaborate ketone starting materials, we could start to see different products that would be possible from this reaction. So for example, if I use this ketone and I go through the same process, I now have two different hydrogens that I can extract. And so that is going to give me two different enolates that will form. So this is one possible enolate. This is the other possible enolate. So that's just taking like HA versus HB. And then if I have those different enolates and I treat this with an electrophile, like ethyl iodide, I'm going to get either that product or that product. So those numbers are relatively close to each other. When the pKa's on either side are similar, what does that establish? What do you get if the reactivity to the left and the reactivity to the right is similar? You get an equilibrium established. So the reaction is reversible in that process. And so what happens is, yeah, you may go grab that easy to get hydrogen first, but then you might give it back too. You're going to go back and forth, back and forth. But eventually, this gets the more stable option. And so eventually you settle with that more stable enolate forming. The equilibrium gets established and ends up favoring the more stable equilibrium. So we use a weaker base. It makes the reaction reversible, and it favors what we call thermodynamic enolate because it's the more stable enolate. So this will form if we're using potassium terbutoxide. If we use an irreversible base, so when the pKa is 38, that's going to grab a hydrogen and it's not giving that hydrogen back. There is no equilibrium established when I use LDA. It's a completely irreversible reaction. So LDA goes in and grabs that easy to get hydrogen, and it does not give it back at the end of the story. And so what that means is that you're going to end up with what we call the enolate. And that's the fast one, the more. That was the easy one. And so depending on the base that I use, I can get a different enolate and that will result in a different final product. And that is all helpful. potassium terbutoxide, but that could be LDA. It will not change anything about my answer. But I'm going to add one of those carbon chains on the left-hand side, so I'm just going to do the methyl iodide.